today's keynote title. The title for today's presentation by Mr. Fuller is Gateway, Humanity's First Lunar Space Station. And with that, thank you, Mr. Fuller, for being here. Take it away.
Well, thank you, Dr. Drexler, and it's wonderful to be with you all this morning or afternoon, as the case may be. Like you said, my name is Sean Fuller. Happy to be here representing NASA and the Gateway, but also beyond that. And some of what I'll talk about from Gateway is that international partnership that we here in the U.S., but our partners around the world, advancing humanity and taking human exploration beyond low Earth orbit. So real pleasure to be here. Look forward to kind of talking about some of the things we've built on in the past. I love the title of this seminar, From Skylab to Gateway. And so I'll talk about Gateway, but how we're building off of Skylab for that as well. And certainly some Q&A at the end there as well. So let's see if we can go on to the next slide. Just a little bit of a background. Certainly you hear of Artemis, and that really is our next exploration and next phase. And I like to say that, we're building upon the past. Apollo was wonderful missions in the 70s. That were scouting missions. We learned a lot. And now for that next phase in Artemis, we're really taking our experience from the last several decades, expanding human exploration, going on to the moon, taking advantage of a lot of things we've learned about on the moon, a lot of new science interest in there. And so we'll be exploring the South Pole, but also always looking out to the future and our horizon goal, if you will, and that is Mars. And so we talk about it as being Moon to Mars. And so I'll give a little flavor of how we're taking Skylab and advancing that forward to Moon to Mars and building those capabilities and technologies to set those first boot prints on Mars in the not too distant future. I think folks are very familiar with Artemis as overall and that next step in taking beyond Apollo era. So if we can go to the next slide, really one of that linchpin in it, in a program that I'm so proud to be a part of and working on with our partners around the world, that is the hub for Artemis, is Gateway. As that point where crews will go to and then step off in the future to the lunar surface, or like I mentioned, moving on to Mars as well. It's really a central hub as that station that enables it, but it certainly had a beginning in the past. And so if we can start there on the next slide, we talk about we often say that we stand on shoulders of giants, and that certainly is the case in the work that I'm doing today, the work that's going on in low Earth orbit today on the International Space Station, built off of Skylab. This is a historic year. 50 years ago, this past May, the Skylab 1 crew entered Skylab and really started our first foray into longer duration missions above the Earth. That really started that learning cycle of humans living off the planet, something we obviously hadn't done before that, and that we continue to build upon and learn today. These are beautiful graphics that kind of remind us from those early days, but things that we're still working to conquer today. When I look at this, I'm reminded that first Skylab, one of the first things that they had to do was a repair mission to enable Skylab for those future crewed missions. And so certainly taking some of those lessons learned there, but also the big part that we're learning, and I believe Dr. Polk had a presentation about the human effects and started with Skylab. You see here the Skylab 1 crew in their exercise devices and really learning how crews and people can live off the Earth for longer duration periods. Certainly things that we build upon that served as a foundation for us as we built the International Space Station and had crews living up there and still do, but as we advance it forward into the Gateway as well. So we go back and look at history and our lessons learned, what we've learned over that time frame, the technology advancements, but also the technology gaps that we have to close as we go for longer duration lunar missions, but also those long transits out to Mars, on Mars, and on the way back, really has its roots and its seeds in the foundation that was Skylab for us. And so as we look at that, I like to think about space stations as an evolution, starting with Skylab, evolving to ISS, and then bringing us to the wonderful project that we're in the process of building and be flying soon called Gateway. But if we can go to the next slide, we'll build upon those three Skylab missions, 30, 60, 90-day missions to what we have on orbit today, the International Space Station, and crews that have been living in space for the last 23 years. And I always kind of pause with that and to think about it. I had the great opportunity to talk to some high school students last week and to really relay that. And we have a generation now that the norm is people living off of the planet. I think it's a pretty cool thing. And to think about where we're taking it in the future, where the norm is people are expanding beyond around the Earth to ventures and living outside of Earth and orbit of Earth. And that's pretty impressive and pretty humbling to think about those advancements and what we'll be doing and taking forward into the future. ISS, that, like I said, crews living there for 23 years, but 25 years of operations of ISS will make that mark a little later this year, really advancing the capabilities of crews and humans living in space. The scientific research it's done on the International Space Station, the technology advancements for it as well. We'll have just next week, Frank Rubio will be landing. He will have been in space for over 1 year. That's a kind of advancements for both human health as well as the technology and the systems that we'll need for these much longer Mars transit durations. If I look at ISS, I'll tell you what I see here is that next phase of cooperation amongst partners. Obviously, here we have the United States, our European, Canadian, Japanese, and Russian colleagues that have built this wonderful space station that we're taking. And in the Gateway program, we take a lot of lessons learned from that as we look to the future. We also use this as an opportunity to do a lot of technology advancements and development to help us. You've probably seen new solar arrays being deployed on ISS. Those same solar arrays we'll be using in Gateway. And so we're using that as that technology advancement, doing some of the testing, building upon the technologies on ISS to get us ready and to build Gateway as we go out. Obviously, ISS, we've got this week, we've got 10 people living on the space station. Usually it's four. We're in the middle of I'm sorry, usually it's seven. We're in the middle of a transition of crews right now. And so it's 10 people living up there, operating, recirculating the life support system, really advancing those technologies that's going to take us farther into the solar system. We're also doing a lot of research on the International Space Station, a wonderful platform. And so we think about Gateway as complementary to that in the future. There's certainly things that are done in research in low Earth orbit, but there are things that we'll have opportunities to in the unique environment that is Gateway beyond that. So we talk at NASA and with our partners, we really look at it as a suite of capabilities stretching across those realms as we expand that exploration, but also as we get ready for out in the future. A couple other things I like to remark about ISS as I look at this beautiful picture. We don't know what we don't know when we start. And that's really something that we take to heart in Gateway. I look at this graphic of ISS as it flies today and see a different ISS than we envisioned when that first element, the FGB, launched in 1998. We have additional capabilities. I mentioned a solar array replacement in the systems, the beam, the expandable inflatable module, commercial space stations that will be coming on to the end of ISS here in the near future, as well as commercial vehicles that have and continue to support ISS. And so one of the big lessons we take out of ISS, looking to Gateway, is we don't know what we don't know yet. And so building in that modularity, that flexibility, and the capability into the future is one of the big lessons that I personally take as we get ready and advance it into Gateway and looking into the future. So let's see if we can go on to the next slide and we'll kind of get a bit more into what that future is, and what we're making it today, and what we're looking at into the next steps as well. So I mentioned, Gateway. It's going to be our wonderful space station around the moon, orbiting in the wonderful near rectilinear halo orbit. Certainly a full mouthful there, but a wonderful orbit that balances between the Earth, Moon, and Sun to balance those forces to really put us in a stable orbit that requires a minimal capability to maintain that orbit. It becomes that hub where the other elements of the system can maximize on their capabilities. And so what I mean by that is you see this picture of an Orion approaching Gateway. In the design of Orion and SLS, we maximize that for crew transportation from the Earth to Gateway. And so it can focus on those pieces and really hone in on that. Whereas the landers that will go from Gateway down to the lunar surface we'll maximize those designed for that portion of the mission. And so by doing that, we increase our capabilities, and each one of them is best suited for its phase of it. Gateway becomes that hub where we bring these elements together and enable the different pieces to it. In the future, it has that capability for expansion and growth to have a Mars transit, as we call it, HAB, that could be built at Gateway, crews come via Orion or future crewed vehicles to Gateway, then get into Mars Transit Hub and go on out to Mars on that year or so journey out to Mars and then back through Gateway as well. And so we really use that to maximize our capabilities, different elements of the system, and stitch those together with our resources. Gateway also being in its orbit is a new unique platform for science and research outside of the Van Allen belts, outside of low Earth orbit, a completely different viewpoint on heliophysics as well as into deep space for a human platform that we haven't had before. So now, while we have crews that visit for durations of 30, 60, perhaps up to 90 days at Gateway, we're doing science on Gateway 24/7, 365 in that new platform. And in fact, one of those advantages, if you will, of those crew visits and the time, the quiescent time without it, is a very pristine microgravity environment. And so enabling that research as well, it's going to be a wonderful platform for that around the moon, but then also supporting us as we get ready to move out further into the solar system. And so to dive a little deeper into Gateway and some of that technology that we're advancing and building and getting ready, if we can go to the next slide, I'll kind of walk through the various elements and pieces of Gateway and what it is. Like I said, this is part of a partnership with us and our partners around the world, building off of some of our history and experience, but also with that eye to the future in advancing those capabilities. So I'll just kind of walk us down the elements of Gateway, starting on what you see as I'll say the left-hand side of the slide with the PPE, the power and propulsion element from Maxar, based on what they commercially have as a 1300 COM-bus, as we call it, but certainly a lot more capabilities within it. As we look out into that future and supporting a space station like Gateway, the solar arrays, I mentioned a lot of heritage from ISS, much bigger than you would have on your normal COM bus. And so advancing that technology and building those solar arrays to provide, you see the two arrays there, they'll provide us 60 kilowatts of power for Gateway. Certainly big advancements, and we look at that being more efficient with solar arrays as that technology advances. One of the major advancements is the solar electric propulsion that is a part of PPE. Hall effect thrusters using xenon, the biggest thrusters that we'll produce, 12 kilowatts. That's really pushing the edge. We'll have 3 of them as part of PPE that will be used to maneuver and control Gateway on its way out to orbit and then in orbit around the moon. That's an advancement that's going to be really important for us. High ISP engines for architectures in the future as we look at transits, most efficient transits to Mars for different hardware, for example, with engines such as that can add that capability. So that first piece, what we call PPE, being built by Maxar in California right now. A lot of pieces of it are in the assembly phase with the central cylinder and elements within that. Solar array cells are being assembled right now into the arrays as we talk about. That becomes one of the first elements that will go into launch. The next part of it, the next module down the line, if you will, what we refer to as the HALO, or the Habitation and Logistics Outpost. That's a first habitable element being built by Northrop Grumman. It has a lot of heritage as well from the International Space Station. It's a 3-meter diameter element built off of the Cygnus module that's used to resupply ISS today. It's bigger, longer, with radio ports on it to enable additional capabilities, but it has that heritage. That's one of the things that we're really looking to take advantage of within Gateway. I talked about the Maxar bus and then this heritage within Halo. It helps us hit the ground running a bit faster with those designs in place and some of that manufacturing, just adapting it for our future capabilities. And so that's going to build us into that first module for crew habitation called Halo, but it includes other elements to it as well. You see labeled on here from our Japanese and European colleagues elements to Halo, including a lunar comm system. So Gateway is going to be in its orbit around the moon. Not only is it supporting the crews coming and going to the surface then, but also comm relay. And so with Gateway, it becomes that relay station. If you think about on the South Pole, the line of sight back to Earth can be a very low elevation, cause some challenges and even some blockage at times with comm back to Earth. And so Gateway in its orbit in the NRHO, about 70,000 kilometers above the South Pole at that phase, becomes a wonderful relay station for it back to Earth. But another part of Halo that you don't see in a graphical picture is the software that's built into it as well. One of the big areas that we're looking and advancing from where we sit on ISS today, we call it the Vehicle System Manager. It's the top tier software that'll be controlling Gateway, but with a lot more automation in it. On crews on ISS, we have crews there all the time that can respond. Clearly, that's not the case on Gateway or on future expeditions. And you have crews that are venturing away from the home vehicle. Perhaps all the crews are leaving away from that home vehicle. And so the software and the software automation and control is going to be very important. That's one of the areas that we're also pushing in the technology development realm. Both PP and Halo, those will be integrated together and launched on a Falcon Heavy rocket towards the end of 2025. We'll use those solar electric engines to push PP and Halo out into its orbit. It's about a year's worth to get into orbit around the moon. That's a great test bed of those engines and to really flex those out, those 12 kilowatt engines, and to get a great performance and runtime on it. As us in the commercial industry will look at those as very highly efficient for future applications as well. Moving beyond in elements of Gateway, then we really get into the heart of the Gateway and the partner contributions, the international habitat from our European colleagues. That's going to be the key ECLIS or life support functions within Gateway, contributed there by our Japanese colleagues. That will be a kind of the home base, if you will, for the crew. It allows us, again, I talked earlier about maximizing components, the life support systems in IHAB, which become part of Gateway's life support systems. That lets us get off of the Orion life support systems. So now we're enabled with longer duration missions. Orion has about 21 days of capability of life support. Crews come to Gateway utilizing IHAB, much increased life support capabilities with the CO2 reduction system, oxygen supply, whatnot within IHAB. That allows us to expand our duration of missions at Gateway. And then also it translates into expanded duration missions down to the lunar surface as well as we do that. Adding on after that, I mentioned the PP as it provides solar electric propulsion, but you got to be able to refuel that as well. That is what the Esprit refueling module does. That too is an advancement in technology for us. It is refueling of xenon and also bipropellant that is in PPE. Longer fluid lines and runs for that that we haven't had before, but certainly something that we will need if we think about future expeditions much farther out into the solar system and that need for refueling. So the Esprit module, that's going to provide that for us and add capability for future refueling. You know, similar to ISS, we designed Gateway for a 15-year life, and I like to say ISS is doing pretty good 25 years into its 15-year life. Part of what enables us to do such a thing on Gateway is that Esprit refueling module, expanding the capability that will continue to use it for the life that's needed for Gateway. Adding elements beyond that, you see the robotic arm from our Canadian colleagues, also referred to as Canadarm3, the third generation, first generation on Space Shuttle, second generation that is used on nearly a daily basis of ISS, and then a third generation here on Gateway, but also looking at that eye for the future. This arm on Gateway is going to be much more automated than we have operating on ISS today, but it also has a wonderful capability, I say, of self-repair. So on ISS, if we have an issue with the joint, it's a crew that goes outside on a spacewalk to service it. That takes away from crew time for research as we talk about an exploration, it takes away from crew time on the surface if we have to do a spacewalk. This arm, the design of it, allows it, between its functions of what we call a big arm and a small arm portion of it, to do self repair on any joint, to remove it and transfer it through a science airlock internally, where either it's swapped out with a new component or a crew there can do maintenance on it. Again, as we think about that automation and what advancements we need for the future, which kind of leads to that next and final major core element of Gateway. That's the airlock, both for crew and, as I mentioned, we call it as a science airlock for transferring things internal and external. Certainly from a science perspective, but also for maintenance there as well in those capabilities. And of course, you can't have a space station without the crew arriving on Orion or logistics support from either our domestic capability, our contract with SpaceX, or also our Japanese colleagues with what they refer to as HTBXG, which appropriately HTBX will be a resupply vehicle for ISS beginning next year. But a gateway version, the G, is that evolution for us in resupplying at Gateway. With the capabilities there, it gives us a resupply. That's really where we get the 60, 90 day. Those are the limits. Is a resupply is really what limits our crew duration. They're on Gateway or supporting it under the surface as well. If we go to the next slide, I mentioned that science is very important for us. We'll start that early on as we transit out that first element launch on the Falcon Heavy. That'll include radiation monitors external from both NASA and our European colleagues that'll look at solar radiation as well as galactic radiation. And then internally, internal dosimeter array that'll look at radiation internally. That's one of the big things that we have to combat operating outside of the Van Allen belts as we get ready to go deeper into space. So right from the get-go on Gateway, we'll be doing that, adding that more data for the research community, looking at those pieces coupled with the human effects and the human mitigation of it. We'll also, in addition to having multiple external platforms outside of Gateway, you see that the lockers here at the bottom will have 16 different research platforms internal in the pressurized volume as well. One of the things that I'm excited about is microgravity and the crystal growth and the activities that are happening on ISS today. This is another platform for it. Without the crew there several months, it gives us an opportunity for microgravity where you don't have the perturbations that may come from the crew activities on Gateway. So looking forward to a lot of great advancements in research in that as well. But we're moving in those directions today. And so if you can go to the next slide, very excited about Artemis 1 and its mission last year. Fantastic mission, sent that vehicle 40,000 miles beyond the moon, the farthest out of a human-rated vehicle. A tremendous 25-day mission that returned. We learned a lot about operating in that, operating Orion. It's a much bigger spacecraft than Apollo was. It'll carry 4 crew. A lot of good shakedowns in that test flight. It gets us ready on the next slide for Artemis 2 and the crew that is preparing for that mission that will go latter part of 24 as they get ready to launch and have that crewed shakedown mission of the Orion spacecraft. And I really like this picture. It shows our 4 crew members of Artemis 2, Reed Wiseman on the left from NASA, Victor Glover, Christina Koch, and then on the far right is Jeremy Hansen from the Canadian Space Agency. A beautiful picture really representing the diversity across NASA and our partners as we get ready to do that exploration. You know, we have a phrase that we often use, and that is we go and we go together. And that's really kind of what I see here. Folding in our partners, we're all a part of it. We each pool our resources to make this possible in Artemis, starting with Gateway and then looking much beyond that. So looking forward to that on the Artemis 2 mission. Artemis 3, the first landing, while at the same time we're starting to build those initial capabilities of Gateway, and then the Artemis 4 mission and the subsequent missions that will initially add those modules to Gateway, but also be used for those longer duration crew surface stays because we have the capabilities that I mentioned on Gateway that allow us to expand that. So really exciting. We've got hardware in production on Gateway in California, that Halo element in Italy coming together very nicely. We'll get that shipped over summer of next year with Northrop Grumman, be integrating the pieces within Halo and getting it ready for the launch. So we have hardware, looking forward to putting it in orbit, and then looking to these crews that will enter Gateway there in the future and really expand us. So if we can just go to one more slide, we'll leave it with ways to connect on the socials. And Dr. Drexler, I'll pause then for questions.
Sounds good. Thank you so much for your presentation. Did somebody have a question? No, there's one question in the chat that I can read to you. The end of it says, in what ways does Gateway address the important political role of space technology collaboration? Let's talk about international context.
Yeah, so it's broken up a little bit there, but I think the
Were you
question
able to
was,
hear me?
yes, I was. I think we're talking about the political importance of it. And thank you. That's a great question. At NASA, we have the Artemis Accords. Very happy to have Germany signed on last week, 29 nations now. I really think if you look at this and you see it reflected in Gateway, and you'll see it in many other elements of Artemis, it is that human endeavor to press ahead. This isn't just NASA. This is NASA led, but our international partners. It shows that forging together, taking humanity beyond, sustained return to the moon, but also exploration on the Mars as one integrated international partnership. I think that's critically important. As we look at it, we see the importance in how that's happened with the International Space Station, that we say in space there's no borders. You see that exercise today in the ISS partnership and expanding it broader as we press forward in exploration. So it's a key part of it. You see it reflected in that first crew of Americans and Canadian as well, and you'll see it in all the future as well.
Cool, that's great. And that was from William Stewart, that question. Thank you, William. And we have time to sneak in one more question. I also had a question, but if we don't have time, that's okay. Melissa West, she asks, are there any special technologies used to protect Gateway from solar events?
Yeah, it's a great question. And at this point, we're not using any particular new technologies, if you will. The radiation protection that comes within the systems for it, that's part of the duration. And so it's not crews on longer duration like we have going to Mars, but that's part of the capabilities that we'll add in the future. So we look at it. We have certainly systems in place within Gateway and within Orion for high solar activity events that might happen. We're in a solar maximum now. So when the crews go, it'll be coming off of that. But for solar flares and type events to protect for it, but then also to look ahead to the future and fold those into systems. Can accommodate, there's a lot of research going on solar shelters, for example, or radiation shelters that could be incorporated. That's kind of where I talk about the unknown unknowns and the flexibility in the design of Gateway to enable such in the future.
Okay, thank you so much. I'll sneak in one more question, but if everybody has to go, that's okay.
Absolutely.
But I did have this question for our students in the audience. If you were to recommend, if you were to recommend, what is the most pressing research need in terms of coursework? Did you hear that, Sean?
Yeah, I think so. The most pressing need in terms of coursework, I think, is what I got. Sorry, it was breaking up, but I think that's the heart of it. You know,
Yeah.
as we look in that future in the exploration, there's a lot of it that's going to be on the biomedical side, taking humans and going beyond. We have a lot of experience with crews living on space station for 6 to 12 months. But as we look into the future, going to Mars where there isn't someone there to support on the ground. When crews land on the Earth, like we'll see next week with Frank's return, that there's folks on the ground ready to support that. As we go farther into space, it's not going to be there. We're doing a lot on space station. We're going to be doing a lot on Gateway too to combat that with the exercise of the radiation environment. But that's certainly a very big piece of it. The others, in terms of technologies and those advancements, integrated advanced systems are really what's needed. Getting stuff into orbit, the expense you pay in terms of energy to get off the Earth mass is a very big driver. And so we look at that. Well, also, there's a lot of great capabilities coming with 3D manufacturing. And so we think about that in terms of if you're going on a long duration mission, you may not have all the tools or the replacement parts, if you will, with you, but what technologies can we advance to do that in situ, as we say, in place to build upon that? So certainly that the advancements that you see, I talked about software and propulsion, that's really going to be key for us as well as we look farther into space.